So we've talked a lot about what equilibrium looks like, but now we want to spend some time talking about what it means to shift to equilibrium. What happens on the way there when the chemicals are reacting. So shifts to equilibrium happen all the time. When we mix reactants together, reactants, products, whatever, we throw some chemicals in a beaker or a reaction vessel, they will not be initially at equilibrium. Right? There is one ratio of reactants and products that defines equilibrium, and then there's everything else. And so if we start with only reactants, only products, or any mixture, they're going to react. The relative amounts will need to change in such a way that eventually the system reaches equilibrium. It always will go to equilibrium. And so we talk about this as a shift in the reaction. This shift is a kind of the relative changes in reactant and product concentrations, and it's relative to whatever the initial mixture is. So equilibrium will always be the same, but we'll see that we can get different shifts in different kind of directions. And so the directions we can see is based around the sides of the reaction. We can either define it as towards the product side or to the right. That's the side of the reaction. We write the products on the side of the arrow, or towards the reactants. Basically, so we're saying, do we get more products present in going to equilibrium? Do more products show up than we started with, or more reactants? Kind of that sort of idea, this towards idea. So let's look at some molecules. We can have this at the molecular level. So SO2 reacting with O2 to make SO3. So SO2 reacts with O2, and then we get an SO3. And so this would be a reaction that would be at an equilibrium. If we're at an equilibrium, we know that we have set ratios of all my reactants and products. The reaction is still occurring. Some reactants are becoming products, but my ratios are staying the same. So we know there's sort of this dynamic equilibrium that we've talked about. There's a set ratio where overall the concentrations don't change over time. But I don't start usually at equilibrium. Usually I start with only one side. So I start with only reactants, right? That's how we've done chemistry before. We mix SO2 and O2. That's what we've defined as the reactants. And we let them react. And so we know if we start with only reactants, we have to make products. And this will continue. Always with the same stoichiometry, making products, until eventually we reach the same equilibrium that was defined for the reaction. It didn't matter that we started with only reactants. The equilibrium that we reached still looks like the equilibrium we showed before. I just copy pasted this slide. So it's the same relative amounts of each of my reactants and products. Now, relative to what I started with, I can see in this case, the product molecules that I would find SO3, there's certainly a lot more of them than when I started with only reactants, right? So product has been created. I could choose a different initial situation where now I only start with this SO3 product. So I mix only SO3. I know equilibrium reversible reactions can still occur. So if I put product in my mixture, I'm going to start getting some reactant. And I know this will keep going. I'll make more and more reactant until equilibrium is reached. That same ratio of Kc determined by Kc will be where I get my SO2 and my O2. Right? I will eventually end up with some reactant molecules. Relative to starting with only product, I now have more reactant present. But the equilibrium is the same. That ratio is still defined by the same Kc value. So these kind of definitions of shifts, right? This idea of different shifts. Equilibrium is always the same, but shift basically describes how does the chemical kind of makeup change as we go from our initial to the equilibrium. What is this shift in relative concentrations in order to reach equilibrium, or when the system is approaching equilibrium and going to equilibrium? And so a shift for a given reaction. We saw in this case, we were looking at this sulfate reaction, or SO2 reaction, right? We saw you can choose two different initial positions and guarantee you get different directions in the shifts, either making more products or making more reactants relative to where you started. The equilibrium is always the same, right? The endpoint is the same, but the relative shift depends on the initial state. So a shift to products means reactant amounts decrease over time and product amounts decrease over time. So SO2 and O2 would be my reactants. We can see they decrease, and SO3 is the product that increases. So if I'm trying to make SO3, this is perfect, right? If I want SO3, shift to products is what I desire. I want to make some SO3. Shift to reactants is then the opposite. The reactant amounts, the SO2 and O2, increase over time, and my SO3 is decreasing over time, the product amount. In this case, if I wanted that SO3, I'd be unhappy. This is not chemistry that I want to have happen. This is not the shift I want to occur. So these shifts are different than the reaction, right? Kc, and the value for Kc determines what equilibrium looks like. Is equilibrium reactant favored when Kc would be less than 1, or is equilibrium product favored when Kc would be greater than 1? So that's telling you relative amounts at equilibrium. Shifts tell you the relative change from the initial conditions. So if you have an initial conditions with no product, and then you make any product, that would be a shift to product. That does not guarantee there is a lot of product present, just more than when you started, more than the initial amount. So Kc purely describes the chemistry. What is the reaction? What temperature is it at? Shift direction depends on where you start and where you go. As an example of this, we want to look at dissolving lead-2 chloride, so PbCl2. So if we look, this would be dissolving into water. So Kc is 1.7 times 10 to the negative fifth. This is less than 1. So this is a reactant-favored equilibrium. Another way we would say this is that lead-2 chloride is not soluble in water. When you put it in water, you do not tend to form separate ions. It tends to stay as the reactant undissolved solid. So if we think about this, not much will dissolve. If I put lead-2 chloride into water, it looks like it's not really dissolved. It's cloudy because the solid is just kind of floating around in it. But some will dissolve. You can figure out that the amount that dissolves is 0.016 molar. Not very much, but some. You started with pure water and pure solid lead-2 chloride. Now you've dissolved some of the lead-2 chloride. You have made some of what we would call our products, right? Those dissolved ions. There are some dissolved ions, so there has been a shift to products. It's not a big shift to products, but there is still a shift towards the product side. So still very much a reactant-favored equilibrium, but because you started with no product at all, any product would still be characterized as a shift towards the product side. All right, moving along, we want to be on the lookout for the rest of the participation videos. If this is your second time through the video, I hope the audio works for you. Otherwise, enjoy the rest of the videos.